Devin Chehak. I'm a meteorologist with the National Weather Service here in Midland. I've been here just under 5 years. It'll be 5 years in June. So towards the end of this severe weather season will be my 5 years here. So still pretty new to the area, but definitely has some experience. We're going to go through several different topics and be kind of quick hitting with them. First one is thunderstorm ingredients. So kind of what do we need for thunderstorms and then severe weather by extension. Cloud identification, so how to ID different clouds. And then we're going to do a quick quiz of you guys. It's a virtual quiz. I'm more of like give you some time to think and then go through each of the examples. Then we're going to do thunderstorm classification and then quickly go into some radar interpretation. Then we'll talk about spar positioning. So what relative to a storm, what might you see and what might you be looking for? And then quickly, a reminder of how to report weather, especially severe weather. And then we'll close out there. So first, starting with thunderstorm ingredients, there's 3 main ingredients we need for thunderstorms. That is moisture. So you got to have moisture to get rain and therefore thunderstorms. So that's the first step, usually a struggle during the early season out here. They need a trigger mechanism, so a form of lift, and that is basically something to get the storms going. Storms need something to help get them going. They don't just pop up wherever. They usually are triggered by something. Then you need instability, or CAPE as we call it, convective available potential energy. That's just the energy for thunderstorms. And then the bonus ingredient, as we call it, is wind shear. And wind shear is what's needed for organized severe thunderstorms, and we'll talk a little bit more about that here shortly. So let's dive into each of these ingredients. First, we're going to talk about moisture. For our uses, we measure moisture with the dew point temperature, which is in degrees Fahrenheit, very similar to air temperature. Generally speaking, as a rule of thumb out here, you want greater than about 50 degrees Fahrenheit for your dew point temperature for any thunderstorms to develop. It's not a hard and fast rule, but that is typically what we would look for as the bare minimum. And then as higher dew point temperature is generally needed as temperature increases. So the warmer it is out, so as we get into the 80s, 90s, and 100s, we might need 55, 60, 65 to really get thunderstorms to develop. And just as an aside, a lot of people are more used to talk about relative humidity when talking about moisture in the atmosphere. So relative humidity is just the ratio of the dew point temperature to the air temperature, and this kind of relates to the higher dew point temperature needed for as temperature increases. Because if you keep the dew point temperature the same to keep getting it warmer, your relative humidity goes down. So that's how that relates. The next ingredient is a trigger mechanism, or lift. So lift helps thunderstorms develop. Frontal boundaries are good lifting mechanisms. So if we have a cold front, a warm front, or typically out here the dry line. Additionally, higher elevations create lift to help generate thunderstorms. So the mountains and plateaus. So Stockton Plateau, down south of Fort Stockton, the Davis Mountains, the Glass Mountains, the Guadalupe Mountains. All those little features in that area do help get thunderstorms going, especially during severe weather season. Lastly, you need instability, or CAPE. Instability is measured, as I said, by convective available potential energy. That's what the CAPE stands for. And you need CAPE for thunderstorms. Basically, by definition, you have to have CAPE for a thunderstorm. There's no magic value of CAPE for thunderstorms, but generally more CAPE leads to stronger thunderstorms. So the higher the CAPE, the more unstable the atmosphere, the stronger the storms have the potential to be. Coinciding with that is wind shear. Wind shear describes the change in wind direction or speed with height. So how do the winds change as you go up through the atmosphere? And wind shear at its base level acts to keep rain and hail out of the thunderstorm updraft, allowing it to keep feeding on warm, moist air. So that's why you tend to get more severe weather with higher wind shear. And again, there's no magic amount of wind shear for severe thunderstorms, but higher values of wind shear tend to lead to increased risks of severe weather. So more wind shear, more likelihood of severe weather if you have instability and the other ingredients for thunderstorms. So let's talk about the different thunderstorm features. First, we'll talk about the updraft. So that's your towering cumulus clouds, might have an anvil at the top. This is where your warm, moist air is feeding into the thunderstorm and rising up through the air and cooling as it condenses. And then that will follow into downdraft, which is the rain-cooled air that falls out from the thunderstorm. Can have hail, can have strong winds, just depends upon the strength of the storm. But in its base sense, it's just basically where the rain cooled air is, so where the rain is falling. To get more complicated than that, if we look at supercell thunderstorm characteristics, you have a much larger storm with a much stronger updraft. This is your rotating updraft that we call the mesocyclone. This might also have an overshooting top, which is basically cumulus clouds that get into the lower stratosphere, and that indicates a very strong updraft, so more shear. You'll also tend to see a big anvil, so that's the clouds spreading out at the top of the troposphere where weather occurs. You'll have your downdraft to the right in this image. That's where your rain and your hail is, and towards the left is your updraft and your rain-free base. So as I said, your strong downdraft is to the right in this image, and your action area is kind of nearest the downdraft and in the rain-free base under the updraft, and that's where you might see a wall cloud and where a tornado would develop. And we'll get into more details of that shortly. I forgot to mention, this is basically if you're sitting south of a supercell and you're looking towards the north. So this is that perspective. So right is to the east and left is to the west, and into the screen is to the north, just for clarification there. So what is a wall cloud? So you might have heard in the other SKYWARN talks, or if you've heard about this, it's a lower cloud base under an updraft. It's where the updraft is stronger. It appears due to lower pressure under that stronger portion of the updraft, which causes condensation, and it slopes upward and into the updraft. So basically, if you draw a line from where it starts towards the updraft, it should follow in that direction. And tornadoes typically form from wall clouds. So that's basically the first step in a supercell thunderstorm before a tornado would ever develop, is you want to see a wall cloud develop. What I will say is wall clouds are very common in severe thunderstorms, and most wall clouds do not produce tornadoes. So wall clouds is just the first step. It's the first thing you want to look for. So here's a close-up of that. Close-up of the action area, wall clouds in the middle of your screen. That's where your updraft is strongest, and it rotates as it goes up through the storm. You may even see a tail cloud or other small cloud fragments called scud rising into the wall cloud. That's just basically showing warm, moist air in the lowest parts of the atmosphere feeding into the wall cloud and the updraft. Another sign of a strengthening storm and strengthening wall cloud. Here's another look at this. So in the middle, you have your action area. To the right, you have your downdraft. So you can see that whole rain-free area is your updraft, your downdraft to the right, and your strongest part of the updraft is going to be where the wall cloud is, where that lower cloud base is. And as I said previously, wall clouds does not always mean tornado. It's just the first step before you are likely to see a tornado if a thunderstorm is going to produce one. So what do you need to check for in a wall cloud to really see if it's potentially going to produce a tornado is you need to see if it's rotating, if it's persistent, meaning is it staying, keeping together as a wall cloud, or kind of dissipating, and is there rising motion? Do you see warm, moist air feeding into it, like those tail or scud clouds? Those are all indications of a strengthening and rotating wall cloud. So unlike a wall cloud, scud clouds are ominous looking but harmless clouds, and they can occur with updrafts or downdrafts. They basically form due to rain-cooled air, but the key giveaways that these are harmless is there's no rotation with them, There's no rapid vertical motion and there's no inflow. They kind of just hang in the sky. So that's usually your giveaway. Also, another good giveaway that's scud cloud is if it's really rain cooled air that's around you and you see this cloud nearby, it's probably because of that as well, on top of these other features mentioned. Another common feature you will see is a shelf cloud. This can be on the leading edge of a line of storms or one large storm, and it's an indicator of strong winds. And it looks similar to wall cloud, but it's slightly different. So it appears as a wedge-shaped cloud, which wall clouds can kind of look like this, but occurs on the leading edge of a gust front. So strong winds and a lot of rain and hail behind it, and it slopes downward and away from the rain and hail. So that's one of the keys, is slopes away from the storm. They also tend to fill the horizon. They usually are, instead of kind of this small portion of the storm, it's usually a large portion of the storm. And they can occur with any type of thunderstorm, and they typically occupy a large expanse of the horizon. So again, to reiterate, shelf cloud or wall cloud. So shelf cloud slopes downward and away from a downdraft, so you kind of will see the rain-cooled air. In the left image, you'll see the rain-cooled air to the right in the downdraft, and you can see that the clouds are sloping away. In the opposite case, you'll see that under the updraft, you'll basically see that the air is rising up into the updraft and not away. And you can see the downdraft is also to the left, but the clouds are not pointing away from it. They're rising up into the updraft. So that slope, either into the updraft or down and away of the downdraft, is your giveaway for shelf cloud versus wall cloud. Next, we'll talk about funnel clouds and tornadoes. So funnel clouds is basically the next step after you get a rotating wall cloud, and typically formed from, as I said, rotating wall cloud, and indicates a tornado is likely imminent. So often they are little cone appendages extending from the wall cloud, not always, but typically, so as in the left image. But they only truly become a tornado when they're in contact with the ground, and that's by definition. And it's a violently rotating column of air in contact with the ground and extending from the base of a thunderstorm. So only when it's in contact with the ground is it officially a tornado. And while in the picture provided on the right, you see a classic cone-shaped tornado, they're not always classic looking or well-defined, and they can be very hard to see and very irregularly shaped, especially at night and through rain. So just keep that in mind, that there are not always going to be these classic Wizard of Oz style looking tornadoes. Adjacent to tornadoes, but not exactly tornadoes, are landspouts and gustnadoes. So landspouts are not associated with a rotating updraft, so they can form with any type of thunderstorm. And the rotating motion originates near the ground, often along frontal boundaries, like a cold front or a dry line even can cause weak little landspouts to develop. The reason why we're not as concerned about these in most cases is they generally are weaker and short-lived, but they still can cause minor damage if they do occur near property. So just keep that in mind, but they're typically harmless, relatively harmless features that form rarely under thunderstorms. A more common sight will actually be gustnadoes, which is on the right. They're associated with the outflow, so the cold air rushing out away from the storm, and they're unattached from the base of the cloud, and they're generally non-severe. Think of them basically as little dust swirls that can easily form in the wind when you get strong winds. A very similar feature in gustnadoes. Another feature you might see, though is often hard to see, is a microburst. And this is associated with the strong downdraft of severe thunderstorms. And it's basically just a quickly descending column of rain, wind, and hail. And they can generate severe straight line winds upwards of 60 to 100 miles per hour, and even some flash flooding. So the analogy I like to use to explain what a microburst is imagine you're holding a large bucket of water and you're staying in your bathtub and you dump the bucket of water over all at once. That's basically what the thunderstorm's doing, where it's going to hit the bottom of the bathtub and splash in all directions. That's essentially what the thunderstorm is doing. So good way of looking at it. So now I'm going to put your knowledge to the test. So I'm going to show you several images, and I'm going to give you a second to think about what you think it is, shelf cloud, wall cloud, funnel cloud, whatever, tornado even. And I'll give about 30 seconds or so for you to think about it, and then I'll reveal what it is. And we'll go through a bunch of these real quick. So what is this feature? So it's where the arrow is pointing. It's that kind of dark area under that storm. Be careful, it might be deceiving. It also might look a little different depending upon your screen, but just take a good look at it. So if you answered downdraft, that would be correct. It is part of a downdraft. It's not necessarily a microburst, but part of a downdraft. And the key way of telling that it's a downdraft and not a tornado is that it's opaque. You can see partially through it. It is not a solid mass. It is rain, and you can see through rain. What about this feature? This one's a little bit more complicated. And then think about your different features that you might see with a thunderstorm in general, and an updraft, downdraft, all that, and how things are pointed. That might help. If you answer tornado, that'd be correct. So in that circle is a tornado there. The larger, on the right side of the image, that larger dark air mass or dark cloud mass is the wall cloud, and basically the entire image in front of you is the updraft. And you can see actually, if you look closer to you, so towards the top of the photo, so closer in perspective, you can actually see this kind of slope upwards, and that's up into the updraft. So you can clearly see the updraft and then the wall cloud and then the tornado under it. But not everything is necessarily as clear cut. So what is this image? And look carefully, because there are some features that are harder to see just because of how this photo was taken. But I'll let you take a guess. So this is a tornado, actually. So it's kind of hard to see, but to the right of that shipping container, you can actually see a little bit of dust being picked up. So this is right as the funnel cloud is becoming a tornado and coming into contact with the ground. And as you can see, funnel clouds don't always just point straight up and down. They can sometimes come out at weird angles. But you can see, again, that lower cloud base towards the middle of the screen, that's your wall cloud. And the entire cloud base that you see in front of you is part of the updraft. What is this image? Now, the hint here is scale. So how big is this? That's the key hint here. Give you a couple more seconds. So this is actually a shelf cloud. So you can see the dark kind of opaque clouds in the background. That is your rain, wind, and hail. And you can see that the clouds are kind of this wedge shape away from the downdraft, away from the rain, wind, and hail. And it also covers a large expanse of the horizon. So all classic features of a shelf cloud. What about this one? This one's a little tricky. I would say kind of, again, look at kind of the different features and how they're pointed. So for this one, it is not a shelf cloud, even though it fills a large portion of the screen. It's actually a wall cloud, just a large one at that. And that is because, as you see in the middle there, that low-hanging cloud, so low area clouds, you can see it's pointing up into the updraft. So the rain and stuff is actually kind of behind the wall cloud or to the right of the wall cloud, and it's actually pointing from the warm, moist air, kind of from where the photo is taken, and pointing up into the updraft. And that whole big expanse of clouds without rain under it is part of the updraft. So just a really big thunderstorm, basically, with a big wall cloud. What about this feature? So it's a series of images, starts like this. Draw your focus towards the middle of the picture, and one key hint is watch how everything evolves. So for that image, for this is a microburst. So as you can see, this opaque kind of ball you see in the middle of your screen is actually just a bunch of rain and wind and hail falling out from the storm. And you can see it falls towards the ground, gets closer to the ground, and then it eventually hits the ground and it spreads out in all directions. Classic for a microburst. And again, the analogy of the dumping the bucket of water basically looks the same way. So next we'll talk about thunderstorm organization. So there's different types of thunderstorms that we talk about. On the left is pulse, then it's multi-cell cluster, then multi-cell line or squall line, as you might have heard, and then supercell on the right. And as you get increasing wind shear, you tend to go from left to right on this image, but you can have a mix of these storms depending upon the situation. And we'll go through a bit of each one here shortly. So a pulse thunderstorm is what we call a single cell storm. It's basically a garden variety thunderstorm, weak wind shear, disorganized, low probability of severe winds and hail, and doesn't last particularly long, 15 to 30 minutes typically. So basically what this is you get the warm, moist air rising through the updraft, and because there's not a lot of wind shear, the rain just ends up falling right back through the updraft, cutting off this source of warm, moist air, and it dissipates. So updraft and downdraft are basically on top of each other, and it just goes up and goes back down. So pulses basically, hence the name. Next, we have a multi-cell cluster. So this is basically, as you get a little bit more wind shear, a little bit of a more moderate severe threat, they can persist for a bit longer, 30 minutes to a couple hours, and they're capable of producing severe hail, usually about to golf ball size, damaging winds, and sometimes even weaker tornadoes, but typically more just hail and winds. And these are basically a bunch of pulse type thunderstorms in different stages. And this is because you have just enough wind shear, just a little bit, to where it keeps the rain from immediately falling into the downdraft, or keeps the rain in the downdraft from immediately cutting off warm, moist air into the updraft. So that's why you get a bunch of different storms in various phases, from towering cumulus to mature stage, which is basically as you get the tall updraft, and then as it begins to rain out, that's the dissipating stage. So again, just kind of an illustration of this, as you have some wind shear, it blows the storm downwind of the updraft, blows the rain and downdraft away, so it helps the storm persist longer. Multi-cell line is kind of your next step up from that. These can persist hours, more of a moderate severe threat again. These are capable of producing damaging winds, especially along with sometimes large hail and weak tornadoes. It essentially, what it is a constant line of mature storms on the leading edge. So your updraft is on that right part of the image, with a continuous downdraft on the backside of the storm. So you basically get a rush of winds and heavy rain right behind the shelf cloud, which is the leading edge and is actually the updraft, and then the rain will gradually weaken until it ends. And your most severe weather will be immediately behind that updraft, immediately behind that shelf cloud. Then lastly, the most intense storms are supercells. These persist for hours, contains a persistent tilted rotating updraft. These updrafts can last hundreds of miles and dozens of, or half a dozen hours, sorry. And they produce a majority of the severe weather. And that includes our very large hail, our damaging winds, and our strong to violent tornadoes. So your baseball, golf ball, or baseball grapefruit size hail, those extreme hail come from supercell. Those big tornadoes you see on like TV or documentaries, those comes from supercells. So these are the strongest of the storms we get. And this again occurs because of increasing wind shear. So just to reiterate, strongest and long-lasting type of thunderstorm is the supercell. And what sets it apart is because of the strong wind shear, contains a rotating updraft called a mesocyclone. Again, has high severe weather potential and can produce very large hail and the most violent tornadoes. So I'm going to go through a visual representation of each of these storms just to kind of reiterate. So a pulse thunderstorm is going to look something like this. So you can see on the right part of the image, kind of a small little updraft going up. You can even see the little bit of cumulus bubbling up. And then you can see the little downdraft on the right as it begins to rain out. And you can actually see that starting to spread out towards the right, back towards the updraft. And soon this storm will dissipate. So this is right as the downdraft is beginning with this storm. And it won't last too much longer. Multi-cell cluster, you might have several of those little pulse type storms in a loosely organized line, something like this. So you can see a little bit bigger of an updraft, a little bit bigger of a downdraft. You can see it's not immediately raining into the updraft, and you can actually see if you look towards the left and towards the right of the image, there might be other updrafts in the area. So again, kind of a bunch of those pulse type thunderstorms in different stages of development ongoing at the same time. Your multi-cell line, the classic giveaway is the shelf cloud. Large expanse of the horizon with a big shelf cloud. You can see all the rain and wind. In the right part of this image, that's the downdraft, and all the clouds on the leading edge associated with the shelf cloud is your updraft in this case. Then lastly, you have your supercell. So you can see in this case, you get this big rain-free base. That's your big updraft. In the center, you have the wall cloud, that lowered cloud base, and even under that, you have the beginning stage of a tornado. So you have a funnel cloud, that large cone shape, and it's just about to come in contact with the ground. So it's shortly to become an official tornado. You can see the strong downdraft to the right as well with this storm. And the fun thing about this picture is you can almost see the rotation of the screen. You can almost see that counterclockwise rotation of the supercell and how the clouds are shaped in, with the storm and kind of that saucer like corkscrew shape. So now we're going to go into some basic radar interpretation. This is more just kind of a crash course, and you can use it with different radar apps. I'm not advocating for any particular one, but if you do have one of the fancier radar apps, this is stuff you can look at. So the first thing you look at, and what you'll see a lot on TV, is reflectivity. This just indicates the returned energy to the radar from objects, rain, hail, etc. So typically your green and yellow colors indicate light to moderate rain. Your red and pink colors indicate very heavy rain or even large hail, depending upon the situation. So that's what you're seeing when you see these different colors. They have meaning. Usually the brighter colors are meant to jump out more because they have, they're more threatening. Heavier rain, potentially large hail, that sort of thing. A step beyond that is you can look at velocity. So this indicates the direction of objects are moving relative to the radar from the Doppler effect. So think of it as a car drives by, how the sound pitches up and down. We can do the same thing with detecting objects with radar. The brighter colors also indicate higher wind speeds. So green colors are towards the radar and red colors are away from the radar. So you have to know where the radar is in the image, but green would be towards the radar, red would be away. So in this image, the radar is somewhere off to the left of the picture. And just in general, bright green and red directly next to each other often indicates rotation. So in this case, you can see between Dublin and Wingo, those bright red and green colors are directly touching each other, that's indicative of strong rotation and actually a tornado in this case, which we'll get into shortly. So another thing you can look at that's more advanced is called correlation coefficient. This is basically the correlation or the relationship between height and width of objects detected by radar. So where you see all these red colors is where the values are close to 1. So what that means is the object is about the same height as it is wide. So think of a raindrop. But as you start getting towards yellow and green colors, that indicates more irregular shaped objects. So potentially hailstones, sometimes like sleet or graupel or any kind of frozen precipitation that has irregular shapes. Those will sometimes show up in yellow and green colors. And blue colors indicate randomly shaped objects. So in this case, tornado debris also can indicate bugs or other types of as we call it, non-meteorological or non-weather related objects will show in these blue colors in correlation coefficients. So let's take a look at what this might look like in a series of images for a tornado. So you can see in the left, you have a reflectivity image. You can see this strong area of rain and hail in the red and pink colors. And you can even see it kind of has this hook-like appendage. That's what we call a hook echo. That's where your strongest part of the updraft is. That's where your wall cloud would likely be, and that's where a tornado would potentially develop. So if you see a hook echo, that's your action area as we showed earlier, and that's what that would look like on radar. To the right, you see velocity. You can see general pattern of green and red relative to the radar being to the bottom right of this image. And you can see there's green and red immediately touching each other, bright green and red. So again, green is away from the radar, red is towards the radar. You can see that's kind of showing counterclockwise rotation, and that is in fact a tornado in this case. So you can see that rotation where those green and red are right next to each other. You can see how it causes that counterclockwise rotation. And this is specifically the Sterling City, Texas tornado from a couple years back. That was just as it crossed out of the Midland, Odessa area into Sterling County. And you can see this very classic storm, big updraft, see the wall cloud in the middle, and then the beginning stage of the tornado in the center part of the image, that cone shape. So putting this all together, here's radar interpretation for a classic supercell. So we're looking at this image or this area towards the center. So you can see high reflectivity values indicating heavy rain and hail. You can see in velocity in the upper right that these strong winds moving towards and away from the radar are immediately touching each other. You can see that correlation coefficient is in the blue color or lower, indicating potential tornado debris. And then we're not going to talk about the bottom right image. That one gets a little complicated. But you see this classic hook echo shape. You see this kind of, and all these different features co-located with each other, so located in the same part of the storm. So where you see at the tip of that hook echo, you see that ball, and right where that ball is, you can see that there's strong rotation. Where that strong rotation is, you see the lower correlation coefficient, all pointing towards an ongoing tornado. And this is in fact the Mayfield, Kentucky tornado from a few years ago. So very intense tornado in this case. But not all supercells are as easy to spot. So this is an example of a non-classic supercell. So take a look at these images. So what you'll see is, towards the center of this image, you'll see that there is some higher reflectivity in the reds. There's also this little area of strong velocity, the bright reds and greens immediately touching each other. And there's also a little ball of blue in the correlation coefficient in the bottom left, showing potential tornado debris, and they're all located in the same spot. And that is actually a tornado we had near here a few years back as well, near Pleasant Farms. And this is an example where it doesn't have a classic hook echo shape on radar, though you can kind of see one. If you kind of look carefully, you can see a little bit of that hook shape kind of in the center left part of the image. But the key thing to identifying potential tornadoes on radar is just seeing if all these features are located in the same part of the storm. That's the key thing. So let's just see if all radar signatures are located in the same location, because it can be kind of tricky. So we'll look at this case. Oops, sorry, went too far. Spoiler. So you can see we have this hook echo shape in the reflectivity in the upper left. You have seemingly strong velocity, the green and reds immediately touching each other. You even see that there's some lower correlation coefficient in the lower left. The blue color is located in the same general area. So what gives? Why isn't this maybe a tornado on radar? Well, they're not all co-located with each other. So that strong velocity and that lower correlation coefficient is actually a radar artifact of just a strong updraft. So actually what you're seeing in the correlation coefficient is bugs and dust being ingested into the storm due to the strong updraft. So it is a strong thunderstorm, and it is severe most likely, but there is no tornado in this case, at least based on radar alone. So just keep that in mind, that the key thing is everything needs to be located in the same part of the storm. So another Sterling City, Texas supercell. At a glance, it looks like there could be a radar confirmed tornado, but these signatures are not co-located and in the right part of the storm. So just something to keep in mind, that you want everything to be located in the right part of the storm on top of each other. Another thing you can look for is large hail. So you can see kind of have this very classic hook echo shape, though it's not a full hook. You can see that there's pretty strong velocity. Ignore some of the busier velocity kind of in the center part of the image. That's unfortunately an artifact of large hail. But you will see oftentimes that in correlation coefficient, you'll see a lot of those yellow, greens, and even some blues sometimes are very large hail, co-located with the high values of reflectivity. And what you'll also see is extending away from the storm down from the radar beam. So the radar beams pointing towards the bottom of the image, radar beam towards the north or top of the image. You'll see these kind of weak reflectivity signatures extending away from the storm, and then you'll see this like jagged blue appendage of correlation coefficient extending from the storm. What that actually indicates is very large hail causing a hail spike, also known as a three-body scatter spike, due to hail, and this is caused because hail is being reflected part of the radar beam into the ground, wet ground in this case, and then that wet ground is reflecting back towards the radar. And that extra distance it travels is interpreted as the rain and hail being far away from the radar. So because of those combination of factors, the large hail is basically making the radar think that there's rain far away from this, further away from the storm, when in reality, it's just an artifact of very large hail within the thunderstorm itself. So if you see this feature, what we call a hail spike or three-body scatter spike, you want to take it seriously. That usually means very large hail is in progress with the storm. Another feature you can have is the rear flanking downdraft. These are short for RFD, rear flanking downdraft, are strong winds that wrap around behind the supercell updraft. So often right adjacent to and behind the wall cloud is where the RFD will form. It's not always particularly strong. It doesn't always have rain or hail in it, but sometimes it can be particularly strong. And they can, rear flanking downdraft winds can often be severe and cause damage. So for example, when that supercell passed very near the airport on May 31st last year, a fair bit of the damage that was caused was not directly the tornado, but was actually the rear flanking downdraft winds. They toppled a bunch of power poles west of the airport. And That was the rear flanking downdraft. And these radar winds can show up on radar as a fine line extending out from the storm. So you can see in the bottom right image that kind of fine line extending out basically from the hook and to the left behind the storm. That's not always on radar, but if it is close enough to the radar, you can often see the rear flanking downdraft on radar. So we went through all this storm identification and radar interpretation, and now we're just going to kind of reiterate why spires are important. So I showed you all that radar interpretation, but again, most often the radar is only seeing the middle to upper parts of the storm. A storm spotter can really see what's going on underneath. So we can have a general idea of what's going on based on radar, the mid to upper level of the storms, and have a general idea of what's going on below. But it's always good to have ground truth. So with that in mind, and you're spotting, and you're positioning yourself, what does this look like from different parts of the storm? So we're going to have a classic supercell in front of us with a hook in the center part of the stream. Supercell is generally going to be moving from west to east, and your action area is going to be the red circle, and your heavy hail, heavy rain, and damaging winds is going to be the red and purple area. And we're going to basically show what it looks like to be on different sides of the storm. And this isn't advocating to, put yourself in different positions. This is just telling you relative to the storm, what might you see and what might you expect. So if you were to the north of the action area and the hail and heavy rain, and you look south towards the action area, all you're going to see is just an opaque mass. You're just looking through all the rain, wind, and heavy rain, wind, and hail. You're not going to see a whole lot. You're basically not going to see anything in 99% of cases. So you're not going to see much from that side of the storm. But if you move east or directly in front of the storm relative to its motion, so remember moving west to east, unfortunately, that puts you directly in the path of the action area. So if there is a tornado ongoing, you're in its path. So not a safe place to be. You will see if there is a tornado going, but you're also in harm's way. So just keep that in mind, that you either want to get out of harm's way or seek shelter immediately if you're directly in the path, if there could be a tornado with it. There also could be hail and damaging winds because you're close to the downdraft as well, and if there's a strong rear flanking downdraft behind the action area, behind this tornado in this case. If you move to the southeast, again, storms moving from west to east. You're now just to the south of the storm, so move harmlessly to your north, pass by in front of you. So you'll still have a good view of the action area, and you would be able to see a tornado if one's ongoing, but you wouldn't be directly in harm's way. You would be in a safe part of the storm and wouldn't necessarily have anything to worry about other than maybe lightning. Now, if you move to the south or southwest side of the storm, the issue becomes you start looking at the action area still, and the storm's still moving to the north of you or away from you, but you're also starting to have the heavy rain, wind, and hail. That opaque area is now behind the action area, and depending upon the exact conditions and how much rain and hail there is, it can be low contrast and hard to see anything. So you can faintly make out in this picture a wall cloud kind of in the center part of the screen. You can see the right edge of it, but you basically have no idea what's going on in the action area. You can't really see anything. It's all kind of a gray, dark mass. So not always the case, but can be a problem if you're directly south or southwest of the storm. But with all that said, I just want to say that you should observe and identify responsibly. If you have experience and you're out on the roads and want to stop and take some pictures and make a report, that's up to you. Just make sure that if you're going to do that, you pull off the road completely. Do not stand in the road. Keep yourself safe. And then if you're at your house, make sure that if you're going to make a report, that you're not in any immediate danger and that you don't need to be sheltering. And if it's safe to take a picture and make reports, do so. You can always make a report later if you need to take shelter, but first and foremost, we care about safety more than anything. So just as a refresher for SPY reports, and we at the National Weather Service need to know the what, the when, and the where. So what type of severe weather is occurring? So hail, damaging winds, tornado, funnel cloud even, rotating wall cloud, just about anything we care for reports on if it could be potentially hazardous. When did the severe weather occur? So, is it currently occurring? Did it occur 15 minutes ago? That sort of thing. Or did it occur yesterday? Or in some cases, you don't know. I found the hail sometime after the storm passed. We can then use radar to estimate when it occurred. But if you do know or have an approximate time when things occurred, we want to know. And we want to know where was the severe weather. So a good rule of thumb is, the nearest city potentially, on a couple miles northwest of the city of Carlsbad or northeast of Midland, or the nearest intersection, or I'm a few miles up or a few miles down the road on Interstate 20 just west of Stanton. Be as restricted as you can. Roads and intersections being the most easily identifiable landmarks for us to be able to know where severe weather occurred. And with that, just going to go over how to report severe weather. So there's our primary phone number for reporting severe weather. That will get you straight to a forecaster. They will take your report, and we will use that for communicating that with the other members of the public, other partners, just making sure we get the message out there on any severe weather that's being observed, including in updated severe thunderstorm or tornado warnings if needed. If you want to send a photo, the best way is to comment with them on one of our posts on NWS Midland's Facebook page, or tweet it at us on X at NWS Midland. We also have a little form on our weather.gov/math page. If you scroll towards the bottom or scroll down slightly, there will be a storm reports button that you can click on, and it'll bring you to a spreadsheet where you can enter the information that you have for a severe report. So any of those ways help, and we appreciate any reports you can give. Lastly, I will just do a quick reminder of our area. So, National Weather Service Midland covers many counties in West Texas and then 2 counties in southeastern Mexico. That's in kind of this yellow-green color. But we are surrounded by many neighboring offices. San Angelo to our east in the pink colors, Lubbock to the north in the purple colors, San Antonio even towards Del Rio in the orange colors, El Paso to the west in the blue colors, and then the green colors is Albuquerque's area. And then in those areas, if you know you're in those areas, those are the offices you should contact. We can always help pass along information as needed if you aren't sure, but just for your reference, these are the counties and areas we cover and what the neighboring offices cover, but we can pass along information if needed. And with that, I thank you for attending my presentation and how you can contact us. Our main phone number is 432-563-5006. You can also go to our weather page at weather.gov/Midland. And then that 1-800 number is that kind of quick phone number to get to a forecaster if you want to quickly submit a report. And then obviously our social media accounts. And thanks again for attending my presentation.